Welcome to the Deep Dive, your shortcut to cutting through the noise and getting truly well-informed. Today, we're plunging headfirst into the mind-bending world of large language models, LLMs. The digital wizards conjuring up AI magic all around us. Think ChatGPT, think Bard. All those amazing systems. They can generate human-like text, answer complex questions, even write code. It feels like magic, doesn't it? But here's the catch, the big challenge. These models are absolutely enormous. Imagine trying to run a supercomputer in your pocket. Or picture sending a massive multi-volume encyclopedia through a tiny soda straw-sized opening. That's basically the problem we face with LLMs in their full glorious form. They're incredibly powerful, sure, but their sheer size makes them difficult to move around, deploy, or use efficiently on everyday devices. They demand vast computational resources, huge data centers, massive amounts of memory, tons of processing power. So if we want these incredible LLMs to become truly ubiquitous, to work faster and cheaper on everything from your phone to, specialized hardware, we have to shrink them without losing their brilliance, ideally. And that's where our deep dive topic comes in today, something called quantization. Okay, let's unpack this. What exactly is quantization? And why is it so vital for unlocking the full potential of LLMs for everyone, especially if you're hoping to run them locally or, on a budget?
That's precisely what we're here to demystify for you today. Our mission, really, is to guide you through the fundamental ideas of quantization. We'll explore its core concepts, why it's become such an essential optimization for these large language models, and how it impacts everything from the literal size of the model files, the download size, to the speed they respond, and even ultimately the cost of running them, which is a big one. We want to show you the practical applications that are really transforming how LLMs get deployed and introduce you to the amazing tools that make this magic happen, all without getting bogged down in, too much jargon. By the end of this deep dive, you'll have a solid understanding of how we make these digital giants fit into smaller spaces without hopefully losing their intelligence.
Okay, great. So let's start right at the core idea. What is quantization? For someone new to this, what's the simplest way to grasp it? Maybe an analogy.
Yeah, analogies are perfect here. Think of it like converting a really high-resolution photograph. This photo is absolutely packed with detail, right? Millions of colors, subtle gradations of light and shadow. It looks stunning, but it's also a huge file. It takes up a ton of storage space on your phone or computer.
Right, we've all run into that. Too many photos, phone's full.
Exactly. Now imagine you convert that photo to a lower resolution version. Maybe one that uses just, say, a few hundred colors instead of millions. You inevitably lose some of those tiny, almost imperceptible details. A little bit of nuance might vanish. But here's the key thing. The picture still looks pretty good. You can easily recognize everything in it. And crucially, it takes up much less space, making it far easier to email, share online, or just store efficiently.
Okay, I get that. Less detail, smaller file. But the main picture is still clear. So how does that map onto LLMs?
It's remarkably similar, actually. In the context of LLMs, quantization means converting the model's learned knowledge, which is really just all the numerical values that represent its understanding of language, its weights and activations.
Weights and activations. Okay, just numbers.
Exactly, just lots and lots of numbers. And we convert them from a very precise, memory-intensive format to a less precise, much more compact format. It's all about making these numerical representations leaner and meaner, just like we did with that photo.
Got it. Trimming the fat, numerically speaking.
Precisely. And to really understand this numerical compression, we need to talk a bit about what numerical precision actually means to a computer. We're primarily contrasting two main types of numbers here, floating point numbers and integer numbers.
Okay, floating point versus integer. Let's break that down.
Let's start with floating point numbers. You often see these referred to by codes like FP32 or FP16. Think of them as incredibly flexible numbers. They can represent a huge range of values, from tiny fractions like 0.0000000001 up to incredibly large numbers like a trillion and everything in between.
So they cover a massive spectrum. How do they do that?
Well, they achieve this flexibility by essentially having a decimal point that can float around. It's a bit technical, but they use parts of their storage for the sign, the main digits, the mantissa, and an exponent to scale it way up or way down. This makes them incredibly powerful for complex calculations, which is why they're standard in science and engineering and, well, AI training.
Makes sense. Flexibility is good for complex stuff.
Right. But all that flexibility comes at a cost. They are memory hungry. A standard FP32 number, for instance, requires 4 bytes of storage. 4 bytes per number.
4 bytes doesn't sound like much on its own.
It doesn't, but if your LLM has, say, 10 billion parameters.
Okay, yeah, that scales up fast. 40 gigabytes just for the parameters. Wow.
Exactly. That memory requirement quickly balloons. Now, on the other hand, we have integer numbers. Think int8 or int4. These are much simpler. They just represent whole numbers like 1, 2, 3, or maybe -50. No fractions, no decimal points floating around.
Just plain old whole numbers.
Pretty much. Because they are just whole numbers, they are inherently more compact. And crucially for performance, they are much, much faster for computers to process. A lot of modern hardware, especially in GPUs and specialized chips, is specifically optimized to crunch integers way more rapidly than floating point numbers.
Faster processing, smaller size. What's catch?
The trade-off, of course, is that they have a limited range compared to floating point, and they can't directly represent fractions. You have to kind of approximate or scale things. But here's the massive memory impact we're often chasing. An int8 number only needs 1 byte.
1 byte. Down from 4 for FP32. That's a 4x reduction right there.
Exactly. And an int4 number requires a mere half a byte.
0.5 bytes. Okay, that's an 8x reduction. That is dramatic.
It really is. So when we talk about quantization, it's essentially this conversion process, taking those flexible but bulky floating point numbers that make up an LLM's learned parameters and transforming them into these simpler, much more compact integers.
So FP32 gets mapped down to int8 or int4.
Precisely. Now, there's a catch. As you might expect, there's always a catch.
The fine print.
The fine print is that this conversion introduces a small error. It has to, right? Because a continuous spectrum of floating point values is being approximated by discrete, stepped integer values, like stairs instead of a smooth ramp. Our entire goal with sophisticated quantization techniques is to minimize this inherent error, while simultaneously maximizing those massive memory and speed benefits that come from using less precise number formats. It's all about finding that sweet spot where the picture still looks good, even if you technically lost a few pixels along the way.
That makes a lot of sense. So we're essentially making a controlled trade-off, giving up a tiny bit of potential precision for a huge gain in efficiency. But my intuition, it still kind of tells me that more precision is always better, right? Why wouldn't we just stick to these super precise floating point numbers, the FP32s, for everything in LLMs? Yeah. What are we missing here? What are the hidden limitations of these seemingly perfect numbers when we're dealing with something as massive and complex as an LLM? Here's where it gets really interesting.
That's a fantastic question, and it really gets to the heart of why quantization isn't just nice to have, but often necessary. While floating point numbers like FP32 are indeed the cornerstone of numerical computation and machine learning, they have inherent limitations. And these limitations become severely magnified in the context of LLMs with billions or even trillions of parameters and quadrillions of calculations happening constantly. It's almost like we're pushing the boundaries of what these older numerical systems were originally designed for.
Okay, so what are these limitations?
First, there's the limited precision itself. Even what we call precise floating point numbers, like FP32, have finite precision. They can't store infinite detail. They can only represent a limited number of distinct values between any 2 points. This means that most real numbers, the ones with infinite decimal expansions like pi or 13, can only ever be approximated.
Right. Like 13 is 0.333
right.
Forever. Computers can't store forever.
Exactly. It can never be perfectly stored in a floating point number. It's always an approximation, maybe something like 0.333333333333483, depending on the system. Now, this tiny approximation error might seem completely negligible on its own. Trivial, right?
Seems like it.
But in a giant LLM where billions of these slightly imperfect numbers interact through countless calculations, these tiny errors can begin to accumulate. They add up.
Death by 1,000 tiny numerical cuts.
Kind of, yeah. And this accumulation leads directly to rounding errors. Because of that finite precision, arithmetic operations, adding, subtracting, multiplying on floating point numbers, often force the results to be rounded to the nearest representable number. After each tiny calculation, the number might be subtly adjusted, rounded up or down. If you perform millions or billions of such operations, which an LLM does in milliseconds, these small errors can add up, potentially leading to noticeable inaccuracies in the final output.
Can you give an example of that?
Sure. A classic example is trying to add a very small number to a very large number. Let's say you take 1,000,000.0 and you try to add 0.00000000001 to it. With standard floating point precision, the result might still be just 1,000,000.0.
Any number just vanished.
It effectively gets lost due to rounding. It's below the threshold of what the large numbers representation can even notice. It falls into the rounding gap.
Okay, I can see how billions of those could cause problems.
And it gets worse. There's something even more dramatic called catastrophic cancellation.
That sounds bad.
It can be. This happens when you subtract two floating point numbers that are very, very nearly equal to each other. Imagine you have two large numbers, maybe the results of previous complex calculations, and they are almost identical. Both might have tiny, insignificant errors from those previous steps. When you subtract them, the leading accurate digits cancel each other out perfectly. And you're left with just the tiny, potentially error-ridden trailing digits. The noise, basically.
So you subtract two very similar, mostly correct numbers and end up with garbage.
Essentially, yes. The subtraction can dramatically reduce the accuracy, the number of reliable digits in your final result, leaving you with something that might be entirely dominated by the previous small errors. The key insight here is that these tiny, almost imperceptible rounding errors, when combined over billions of calculations in an LLM, can potentially snowball into real inaccuracies, making the model's output less predictable or reliable. It's like a butterfly effect for numbers.
Wow. Okay. Any other pitfalls?
One more subtle but important one. Floating point addition and multiplication are non-associative.
Non-associative, meaning?
Meaning the order in which you perform operations can actually change the result slightly. Mathematically, we learned that A plus B plus C should always equal A plus B plus C. The grouping shouldn't matter.
Right. Basic algebra.
But with floating point numbers, due to how they handle precision and rounding internally, these two expressions might produce slightly different numerical outcomes. Tiny differences, usually, but differences nonetheless.
So just changing the calculation order, even if mathematically equivalent, gives a different answer.
It can, yes. For an LLM, this isn't just a mathematical curiosity, it's a practical problem. It means that simply reordering calculations, which compilers and hardware might do for optimization, could potentially lead to different model outputs. This makes reproducibility, getting the exact same result every time, tricky across different systems or even different software versions or runs.
So what does this all mean for LLMs? Let's bring it back. For models with billions of parameters doing countless arithmetic operations every single time they generate text, these tiny inherent flaws in floating point math can snowball, right? They can accumulate over that vast number of computations, potentially leading to noticeable performance drops or accuracy issues. It's not just about saving memory or speeding things up anymore. It's also about managing this inherent numerical noise that comes even with using full precision like FP32. That's fascinating how the very tools designed for precision have their own kind of Achilles heel when you push them to this massive scale.
Absolutely. And these limitations of floating point numbers really highlight why alternative representations, particularly fixed point, can be attractive in many scenarios and why they are often more amenable to the aggressive compression we do in quantization.
Okay, so tell us about fixed point. How does that work?
Right, so fixed point numbers are fundamentally different from floating point. Their key characteristic is that they have a fixed number of bits allocated specifically for the integer part of the number and a fixed number of bits for the fractional part. The decimal point doesn't float. This is often denoted using a qn.n format. M is the number of bits for the integer part, n is the number of bits for the fractional part. For example, a Q8.8 number uses 8 bits for the whole number part and 8 bits for the part after the decimal point. The position of that decimal point is effectively fixed by the format choice.
So unlike floating point, where the decimal can move to represent huge or tiny numbers, here it's locked in place.
Exactly. The magic of fixed point is that it fixes where that decimal point conceptually goes. So a number like 3.14 isn't stored with a flexible decimal. Instead, it's stored internally as a scaled integer, maybe like 3/40 if we had enough fractional bits. The computer simply knows, based on the qn.n format, that the last, say, 3 digits are actually fractional.
So it's like working with integers but remembering where the decimal should be.
That's a great way to put it. This makes the arithmetic operations, addition, subtraction, multiplication incredibly fast and predictable. For instance, if we wanted to convert 3.14159 to a Q8.8 format, we'd essentially scale it up by 2 to the power of 8, which is 256, round it to the nearest whole number, and store that integer. Then when we want the decimal value back, we just take that stored integer and divide it by 256. The result will be very close to our original 3.14159, but probably not exact, which highlights again that the precision is determined upfront by the fixed format you choose. It's very much a what you see is what you get approach, operating within a predefined numerical boundary.
Okay, so what are the big wins with fixed point then? Why use it?
There are several key advantages. First, computational efficiency. Fixed-point math is generally much faster than floating point. It relies on simple integer operations, which are directly supported and highly optimized in pretty much all hardware. Floating-point operations often need specialized hardware units, FPUs, or more complex software emulation.
Faster calculations, got it.
Second, power efficiency. Because the operations are simpler, fixed-point arithmetic consumes significantly less power. This is absolutely crucial for battery-powered devices. Think smartphones, wearables, and embedded systems like the controllers in your car or smart home gadgets. Less power means longer battery life or less heat.
Lower power draw. Very important for mobile and embedded. Makes sense.
Third, deterministic behavior. This is a big one. Fixed-point arithmetic produces deterministic results. The same inputs will always yield the exact same outputs, every single time. This is incredibly important for applications where reproducibility is critical, like in scientific simulations, control systems, or safety-critical software.
Unlike the floating point non-associativity issue we just talked about.
Exactly. Floating point, with its complex rounding rules and that non-associativity, can sometimes produce slightly different results across different hardware platforms or even just different compiler settings. Fixed point avoids that ambiguity. And finally, a smaller hardware footprint. Fixed-point arithmetic units generally require less silicon area on a chip, less complex hardware. This makes them ideal for resource-constrained environments where cost, size, and power are primary concerns.
Okay. Faster, lower power, deterministic, smaller hardware. Sounds great. What are the downsides?
The main disadvantages are implied by the name: limited range and limited precision. Because the decimal point is fixed, fixed-point numbers can represent a much smaller range of values compared to floating point before you run into overflow, number too big, or underflow, number too small. And their precision is fixed once you choose the QM.N format. If you need extremely high accuracy across a very wide range of values, fixed point might not be suitable. Floating point's flexibility wins there.
So it's better for situations where you know the range and required precision up front.
Exactly. It excels when the numerical requirements are well-defined and bounded. Which brings us to real-world applications. Fixed point is heavily used in digital signal processing, DSP. Think audio and video processing, telecommunications. Real-time tasks love its efficiency. It's also prevalent in embedded systems, automotive controls, industrial automation, consumer electronics, where low power, low cost, and reliability are paramount.
Can you give a really concrete example?
Sure. Think of a simple digital temperature sensor. Maybe it needs to measure temperatures from, say, 10 degrees Celsius to 40 degrees Celsius, and it needs a precision of maybe 0.1 degrees Celsius. That's a pretty well-defined range and precision requirement. You could choose a fixed point format, maybe Q8.8, that easily covers this range, much more than 10 to 40, and provides more than enough precision, way better than 0.1. This allows the sensor's chip to be very small, cheap, and consume minimal power, maybe running off a tiny battery for years. Using floating point here would likely be overkill and less efficient. It really shows how this seemingly less precise method can actually be the superior choice in many specific practical computing scenarios.
Right, using the right tool for the job. Fixed point makes a lot of sense in those contexts. Okay, so we've laid the groundwork for what quantization is, touching on number formats like floating point and fixed point, and why floating point numbers aren't always the perfect fit, especially at scale. But now, for the listener, this is where it gets really exciting. What are the actual tangible payoffs of doing all this numerical magic? How does quantization truly change the game for LLMs? This is where it gets really practical, and you'll see why so many developers and businesses are so excited about this.
Absolutely. The practical impacts of quantization are, frankly, game-changing for LLM deployment and accessibility, especially when we think back to our earlier challenge trying to run that supercomputer in your pocket. Quantization is how we start to make that feasible.
So what's the biggest impact?
The most obvious and often most dramatic benefit is the dramatic reduction in model size. This happens directly because we're reducing the bit width. Remember, the number of bits used to represent each parameter, the weights, and often the intermediate calculations, the activations in the model. Think about it simply. If an FT32 number uses 4 bytes and an INT8 number uses only 1 byte, you're immediately shrinking the storage required for every single number in the model by a factor of 4.
4 times smaller, just by switching from FP32 to INT8.
Exactly. Let's put some real quantifiable numbers on this. Imagine a reasonably sized LLM with, say, 1 billion parameters. That's big, but not even close to the largest models out there.
Okay, 1 billion parameters. How big is that normally?
In its full FP32 precision, that model would consume approximately 4 gigabytes of memory just to hold the weights.
4 gigabytes. That's already more RAM than some older laptops or basic smartphones have available.
Precisely. Now, if you quantize it down to FP16, which uses 2 bytes per parameter, it halves to 2 gigabytes. Better, but still substantial. Jump down to INT8 using 1 byte per parameter, and you're at just 1 gigabyte.
Now we're talking. That's much more manageable.
And if you push it even further to INT4, which uses only 0.5 bytes per parameter, that same 1 billion parameter model now requires only 0.5 gigabytes.
Half a gigabyte. That's an 8x reduction from the original FP32.
An 8x reduction. This isn't just about fitting it onto a slightly smaller hard drive. It's about making it physically possible to load the model into the RAM of a typical smartphone or run it on a small, inexpensive edge device like a Raspberry Pi or a specialized AI chip.
So this directly enables on-device AI.
Absolutely. Let's imagine our hypothetical startup again, InnovAI. They're still trying to build their real-time translation mobile app. A powerful LLM capable of good translation might be, say, 13 gigabytes in its original FP32 form.
Forget running that on a phone.
No way. It's simply too massive to fit into the RAM of an average smartphone. Even if it did, it would likely drain the battery incredibly quickly and maybe even cause the phone to overheat. But by quantizing that model down to INT8, bringing it down to maybe 3.25 gigabytes.
Still big, but maybe feasible on high-end phones.
Or even pushing to INT4, getting it down to around 1.625 gigabytes, suddenly it becomes genuinely feasible to deploy and run directly on many mobile devices. This isn't just about convenience, it's about enabling entirely new kinds of applications that were previously impossible due to these resource constraints. It opens up a whole new world of private, potentially offline, on-device AI.
That's a huge benefit. What else? Does it get faster, too?
Yes, absolutely. Closely related to the model size reduction is a significant improvement in inference speed, how fast the model can actually generate a response.
And why is that? Fewer calculations?
Not necessarily fewer calculations, but the calculations become faster, and getting the data for them, it becomes faster. It comes down to 2 main factors. First, lower precision means less data needs to be moved from the main memory, RAM or VRAM on a GPU, to the processor cores where the calculations happen. This movement of data, the memory bandwidth, is a huge bottleneck for large models like LLMs. The processors are often waiting for data to arrive. If you quantize from FP32 4 bytes down to INT8 1 byte, you're literally transferring 4 times less data across that memory bus for the weights. That's a massive difference in how quickly information can flow to the compute unit.
Less data shuffling means faster processing.
Exactly. The second factor is, as we touched on before, many modern hardware platforms, GPUs with tensor cores, specialized AI accelerators, even some modern CPUs are specifically optimized to perform operations on integer numbers much, much faster than on floating point numbers. They have dedicated circuits just for crunching 8-bit or 4-bit integers at incredible speeds.
So faster data transfer and faster calculations on that data.
Correct. For a quantifiable impact, think of it this way. Reducing data transfer by a factor of 4, combined with potentially much faster integer math units, can lead to substantial increases in inference speed, sometimes 2x, 3x, or even more, depending on the model, the hardware, and the specific task.
Can you give a scenario for that?
Sure. Imagine a cloud-based service that offers real-time text summarization. Lots of people are sending it long articles to summarize quickly. If their underlying LLM is quantized, say from FP32 to INT8, it means the service can handle significantly more requests per second, higher throughput, with the exact same amount of server hardware. This directly translates to reduced latency for the users. They get their summarized text back almost instantly. It feels more responsive. And for the company running the service, they can serve more customers without having to buy more expensive servers, which ultimately saves them a lot of money on their cloud bill.
Faster, cheaper, better user experience. Seems like a win-win-win.
It often is. But now we need to address the elephant in the room, the accuracy trade-off.
Ah, yes. The catch we talked about earlier. It can't be all good news.
Exactly. While model size shrinks dramatically and inference speed often improves significantly, the model's accuracy can decrease. Sometimes slightly, sometimes more noticeably. It's not a magical free lunch, it's a careful balancing act. The entire goal of any good quantization strategy is to find that sweet spot. That optimal balance where you achieve the necessary performance, gains the smaller size, the faster speed, while still maintaining an acceptable level of accuracy for your specific application.
And acceptable is the key word there, I guess. It depends on what the LLM is doing.
Absolutely critical. Sometimes maybe a 2% drop in a benchmark accuracy score is perfectly fine for a creative text generation tool, or a chatbot handling casual queries if it means the model can now run smoothly on a user's local laptop instead of needing a powerful cloud server.
That seems like a reasonable trade-off in some cases.
But other times, that same 2% drop might be completely catastrophic. Think about an LLM being used for medical diagnosis, or one providing financial advice, or maybe controlling a self-driving car. In those cases, even a tiny drop in accuracy could have very serious consequences.
Right. You don't want your medical diagnosis bot to be mostly accurate.
Definitely not. The key idea here is that quantization is an optimization strategy, not a magic bullet that solves all problems with no downsides. It requires careful thought, careful implementation, and, as we'll discuss later, careful evaluation to ensure you've made a calculated compromise that meets the real needs of your application.
Okay, that makes perfect sense. That's a crucial balancing act, very application dependent. So we've talked about what quantization is, why we need it. It's huge beta. It's like size and speed and this critical accuracy trade-off. But now the big question. How do we actually do this conversion? What are the specific levers we pull, the actual mechanics of mapping these precise floating point numbers into those less precise integer formats?
Right. Let's get into the nuts and bolts. The core mechanics of the most common type, linear quantization, revolve around a few key parameters. These parameters allow us to scale and shift those high-precision floating point numbers so they fit nicely into the lower precision integer range.
Okay, what are these parameters?
First, we revisit precision, bit width. But now, as a choice we make, this is the fundamental decision. How many bits will we use for our quantized values? As we discussed, it defines the granularity. Fewer bits means greater compression and potentially faster computation, but also more potential for information loss, more approximation error. The common choices you'll encounter in practice are FP32, the original baseline, 32 bits, FP16 or BF16, half precision floats, 16 bits, often a good starting point for optimization. INT8, 8-bit integers, a very common target giving that 4x compression. INT4, 4-bit integers for 8x compression, pushing efficiency but with higher accuracy risk. And sometimes even more extreme things like INT2 or INT1, though those are less common for general LLM weights due to significant potential accuracy loss.
So picking the target number of bits is step one.
It's the first major decision, yes. It sets the fundamental level of compression you're aiming for, like choosing whether your compressed photo will have 256 colors or just 16. Next, and absolutely critical, is the scale factor.
Scale. What does that do?
Think of the scale as a conversion rate or a step size. It's a floating point number itself. Its job is to map the range of your original, potentially wide-ranging floating point values, like from megas10 to plus 10, or maybe megas500 to plus 200, onto the much smaller available range of your target integer type, like 0 to 255 for unsigned INT8, or negative 128 to 127 for signed INT8. The scale dictates how much change in the original floating point value corresponds to a single step, a single increment in the integer representation.
Can you give example calculations?
Sure. Let's say your original floating point values roughly range from megs 1.0 to plus 1.0, and you want to quantize them to unsigned 8-bit integers, which range from 0 to 255. The total range of the floats is 1.0, megas 1.0 equals 2.0. The total range of the integers is 255, 0 equals 255 steps. So the scale would be the float range divided by the integer range. Scale equals 2.0255, which is approximately 0.00784. This means each step up in the 0.255 integer value represents roughly a 0.00784 increase in the original floating point value.
Okay, so the scale connects the two ranges. Why is choosing it so critical?
Because if your scale is too large, meaning each integer step represents a big jump in float value, you'll lose a lot of fine-grained detail. You'll quantize very coarsely. Too much information loss. But if your scale is too small, meaning each integer step is tiny, you might not fully utilize the available integer range. Maybe your floats only go from manager 0.5 to 0.5, but your scale was calculated from managers 1.0 to 1.0. You'd only use half your integer values, like 64 to 191 instead of 0 to 255, effectively reducing your actual precision unnecessarily. Finding the right scale, often based on observing the actual min-max values in your weights or activations, is crucial for minimizing error. It's like adjusting the zoom lens when fitting that wide landscape into the tiny window. Get the scale right to see the most important parts clearly.
Got it. Scale is key. What's the next parameter?
Then there's the 0 point.
0 point. What's that for?
The 0 point is an integer value within your target integer range, like 0 to 55, that is chosen to map exactly to the floating point value of 0 0.0. It's particularly important for what's called AFIN, or asymmetric quantization. This just means situations where either your original floating point data isn't perfectly centered around 0, maybe values range from 0 to 10, not 9 to 5 to +5, or your target integer range isn't centered around 0, like unsigned int8, 0 to 255, which is asymmetric.
Why does mapping 0 accurately matter so much?
Because 0 often has special significance in neural networks, for example, zeroing out connections, re-LU activations. Ensuring that 0 point 0 in the float world corresponds precisely to a specific integer value helps maintain the mathematical properties of the operations. It essentially helps anchor the conversion correctly, preventing the entire range from being shifted inappropriately, which could introduce bias or errors, especially around that crucial 0 point.
Okay, so scale sets the step size, and 0 point anchors the mapping, making sure 0 lines up.
Exactly. With the scale, s, and 0 point z, which is an integer, the actual quantization process follows simple formulas. To quantize a floating point value, let's call it x float, you typically calculate quantized integer value, round x float s plus c. You divide by the scale, round to the nearest whole number, and then shift it by the 0 point.
And getting it back. Dequantization.
To dequantize, to get an approximation of the original float back from the integer, let's call it sync, you do the reverse. Dequantized value s, sync z. You shift by the 0 point and then multiply by the scale.
And that dequantized value won't be exactly the original x float.
Almost never, unless the original float happened to fall exactly on one of the representable points. Because of that round operation during quantization, some information is lost. If we quantize, say, 0.5 using our scale of 0.000784 and maybe a 0 point of 128 for a sign range centered around 0, around 1.5, 0.00784 plus 128 gives us an integer around 192. When we dequantize that 192, 0.00784, 192.128 gives us back something like 0.50176, close to 0.5, but not exact. That tiny difference is the quantization error, the lost pixels from our photo analogy.
Okay, that clarifies the core math. But you mentioned tensors earlier, these big spreadsheets of numbers. Do we use the same scale and 0 point for the whole spreadsheet?
Excellent question. That brings us to the concept of quantization granularity, how broadly or finely we apply these scale and 0 point parameters. The simplest approach is per tensor quantization. Here, you calculate and use a single scale and a single 0 point for the entire tensor, that whole multi-dimensional spreadsheet of weights or activations.
One scale, 1 0 point for potentially millions of numbers.
Yes. It's simpler, it's faster to compute, and it requires storing only 2 extra numbers, s and z, for the entire tensor. The downside is that it's less accurate if the values within that tensor have very diverse ranges. Imagine one corner of the spreadsheet has values near 0, and another corner has values near the 1,000. A single scale might struggle to represent both regions well.
So what's the alternative for better accuracy?
The alternative is often per-channel quantization, or sometimes per group or per axis. Think of a tensor, especially in convolutional layers or attention mechanisms, as having different channels or rows that process different aspects of the data. Per-channel quantization calculates and uses a separate scale and 0 point for each channel or row or group within that tensor.
So different conversion rates for different parts of the spreadsheet.
Exactly. This is more complex, of course. It requires more computation to figure out all those scales and 0 points, and you have to store them all, which adds a bit of memory overhead. However, it often leads to significantly better accuracy, especially when different channels within the tensor naturally have very different value distributions or ranges. It allows the quantization to adapt more closely to the local statistics of the numbers.
When would you choose one over the other?
You generally lean towards per tensor if speed and simplicity are the absolute top priorities, and a slight accuracy drop is acceptable. You'd prefer per channel or similar fine-grained methods when preserving accuracy is more critical, or if you analyze your model and find that the values across different channels vary widely. It's like having a custom conversion rate for different sections of your photo, allowing for better overall quality even after compression.
That's a true deep dive into the how, thank you. It's clear that there are these precise mathematical steps, these parameters like scale and 0 point, and choices about granularity that are all absolutely critical. Now that we know the basics of how the conversion works, let's talk strategies. In the real world, how do models actually get quantized? What are the major approaches used to implement this in practice? How does our startup, InnovAI, building that mobile translation app, actually make this happen? Do they do it before, during, or after training?
That's a great transition because this is exactly where the theory meets real-world application and tooling. In practice, there are three core quantization strategies that dominate LLM deployment today, each with its own set of trade-offs in terms of ease of use, computational cost, and final accuracy.
Okay, what's the first one?
Let's start with the simplest and often the first one people try. Post-Training Quantization, or PTQ. As the name clearly suggests, this method quantizes a model after it has already been fully trained in its original high precision, like FP32. It's conceptually the simplest and usually the fastest approach to implement because you don't need access to the original training pipeline or data, and you don't need to do any retraining at all.
So you just take your finished, trained model and quantize it.
Pretty much. The process generally involves a few steps. 1, you select your pre-trained FP32 model. 2, you perform an optional but highly recommended calibration step. Here, you feed a small representative dataset, maybe a few hundred or 1,000 examples, through the model in inference mode. You're not training it, you're just observing the typical ranges, the minimum and maximum values of its weights, and, more importantly, its intermediate activations as they process the sample data.
Why observe the activations?
Because the weights are static, but the activations change depending on the input data. Calibration helps you understand the typical dynamic range your model experiences during actual use. This calibration information, the observed ranges, is then used to calculate those optimal scale and 0-point parameters we just discussed. 3, you apply these calculated parameters to convert the model's weights and sometimes specific layers for activation quantization to the target lower precision, like INT8, and that's your quantized model.
So it's relatively straightforward. Train first, then calibrate, then convert.
Exactly. And there's even a subset of PTQ called data-free PTQ.
Data-free. How does that work without calibration data?
As you might guess, it doesn't use that calibration dataset. Instead, it relies purely on statistical analysis of the model's weights themselves to estimate reasonable quantization parameters, scale and 0-point. It might look at the min-max weight values directly or use more sophisticated statistical assumptions. This is incredibly useful when the original training data or even a representative sample is unavailable due to privacy concerns, intellectual property issues, or if it's simply too massive or difficult to access for calibration.
Sounds convenient, but is it as good?
The trade-off is that data-free PTQ can sometimes lead to higher accuracy loss compared to PTQ methods that use calibration data. Because it's making more assumptions about the activation ranges without actually observing them, the chosen scale and 0-point might not be as optimal. But it's a great option when data is a blocker.
Okay, let's bring this back to InnovAI and their chatty bot for customer support. How would PTQ work out for them?
Right. Their goal is dual deployment. Cloud servers, high volume, and mobile devices, edge. They first try INT8 PTQ on their 13 GB FP32 model. They run calibration, calculate parameters, and convert. Boom! They achieve a fantastic 4x model size reduction, bringing it down to about 3.25 GB. Inference speed likely improves noticeably too. Great for deployment cost and potentially mobile. However, when they evaluate the accuracy using Perplexity, how well it predicts text, they observe a 20% increase. A higher Perplexity means lower quality, less coherent text.
So it's a 20% hit to quality.
Yeah.
Is that acceptable?
For their customer support use case, where clear and accurate communication is key, maybe that 20% increase in Perplexity, meaning worse performance, is just a bit too much of a compromise. Customers might get confused or frustrated.
Okay, so INT8 PTQ is easy, but maybe not quite good enough accuracy-wise. What if they push harder?
They decide to try INT4 PTQ for maximum compression, aiming for that 8x reduction to maybe 1.625 GB. Even smaller, potentially even faster, sounds great for mobile. They run the INT4 PTQ process. The model size is fantastic, but the accuracy degradation is significant. They might see a 50% or even higher increase in Perplexity.
A 50% increase. That sounds like the bot might start talking gibberish.
It could become noticeably less coherent, less reliable, making the INT4 PTQ model simply unsuitable for their core customer support tasks. It might produce confusing, unhelpful, or just plain wrong responses too often.
So this scenario perfectly illustrates the PTQ trade-off. It's fast and relatively easy to implement, but the accuracy, especially at very low bit widths like INT4, can suffer significantly. You might have to back off to INT8 or even just FP16 if the accuracy hit is too large.
Exactly. It's often the first thing to try, but you have to be prepared for that potential accuracy drop.
Okay, so PTQ is option one. What's the second strategy?
Our second major strategy is dynamic quantization.
Dynamic. How does that differ from PTQ?
The key difference is when the quantization happens and how the parameters are determined. In static PTQ, we pre-calculate fixed scale and zero-point parameters for the weights and maybe activations based on calibration and store them. In dynamic quantization, some parts of the model, typically the activations, are quantized on the fly during the actual inference process. So as each new input data batch comes into the model, the system quickly analyzes the range of values in that specific batch's activations, calculates the scale and zero point just for them, quantizes them, performs the necessary operations, often multiplying with pre-quantized weights, and then moves on to the next batch.
So the scale and 0 point for activations change constantly based on the input.
Exactly. The weights are usually quantized statically beforehand, but the activations get quantized dynamically based on the data flowing through the network right then and there.
What are the pros and cons of that approach?
The main advantage of dynamic quantization is its adaptability. Because it calculates quantization parameters based on the current input data, it can adjust to varying input data distributions. This can sometimes lead to better accuracy compared to static PTQ, especially if your input data is highly dynamic or unpredictable, where a single pre-calculated static range might not always be optimal. It's also relatively simple to implement, often just requiring specific operators in the inference framework.
Okay, adaptability sounds good. What's the downside?
The main disadvantage is that this on-the-fly calculation of scale and zero point for activations introduces a small runtime overhead. It takes a little bit of extra compute time during inference to do these calculations for every batch. This means dynamic quantization might not achieve the absolute maximum inference speed compared to a fully static PTQ model where all parameters are fixed beforehand. Also, while it can be more accurate than basic static PTQ in some cases, it might not reach the same peak accuracy as a static PTQ model that has been meticulously calibrated on a very large and representative dataset.
Can you give a scenario where dynamic might be preferred?
A good hypothetical scenario is in, say, financial time series analysis. Market data, like stock prices or volatility, can change drastically from one hour to the next. A model using dynamic quantization for its estimations could potentially adjust its internal numerical range to better match the current market conditions, whether it's a calm period or a sudden crash. This adaptability could lead to more accurate predictions or risk assessments compared to a static model that's locked into a single quantization range based on historical average conditions. It adapts to the immediate swings in the data.
Okay, dynamic offers adaptability at the cost of some speed. What's the third main strategy?
Finally, we have what's often considered the heavyweight champion, especially when accuracy is paramount, Quantization-Aware Training, or QAT.
Quantization-Aware Training. So this involves training?
Yes. Unlike PTQ, which happens after training, QAT integrates the effects of quantization into the training process itself. The core idea is to make the model learn how to be robust to the noise and approximation errors that quantization will eventually introduce during deployment.
How does it do that? Do you train directly with low precision numbers?
Not quite directly, as training usually needs the higher precision for stable gradient calculations. Instead, QAT works by simulating the effects of quantization during the training loop. It does this by inserting special fake quantization or simulated quantization operations into the model's architecture during training.
Fake quantization.
Yeah, it sounds funny, but these operations take the high-precision activations or weights, quantize them down to the target low precision, like INT8, and then immediately dequantize them back to high precision before the next operation.
Quantize, then dequantize straight away. What's the point of that?
The point is to introduce the error or noise of quantization into the forward pass of the network during training. The model sees the kind of precision loss it will experience later during actual quantized inference. Crucially, while the forward pass sees the quantized values, or rather their dequantized approximation, the backward pass, where the model learns by calculating gradients, typically still uses the high precision values to ensure stable training. This allows the model's weights to adjust during training, not just to minimize the task loss, like predicting the next word correctly, but also to minimize the impact of that fake quantization noise on the final output. The model learns to work around the precision limitations.
So the model adapts itself to be less sensitive to the quantization errors.
Exactly. It learns to be robust to quantization. It might learn to push important values further away from decision boundaries or find solutions that rely less on extreme numerical precision.
What's the big advantage of doing all that extra work during training?
The significant advantage of QAT is that it generally achieves the highest accuracy among all quantization methods, especially at lower bit widths like INT4 or INT8. Because the model has actively adapted to the quantization noise during its learning process, it can often recover most, if not almost all, of the accuracy loss that you might see with a simple PTQ approach.
So QAT gives the best accuracy. What's the catch this time?
The main disadvantage is complexity and cost. QAT requires retraining the model, or at least significant fine-tuning of a pre-trained model. This is significantly more computationally intensive and time-consuming than just running a quick PTQ calibration and conversion. You need the training infrastructure, potentially large data sets, and expertise in managing the training process with these fake quantization nodes inserted. It's a much heavier lift.
It's like painstakingly training our photo conversion algorithm to perfectly handle those few hundred colors from the start, rather than just crunching the high-res photo down after the fact.
That's a perfect analogy. It requires more effort up front during the creation process.
Can we revisit InnovAI's chatty bot? How might QAT help them?
Let's say their INT8 PTQ dropped the accuracy on a key task, like sentiment analysis, from 90% down to an unacceptable 80%. If they then invest the resources to perform QAT fine-tuning, simulating INT8 quantization during that fine-tuning, they could potentially recover most of that lost accuracy, perhaps achieving 88% accuracy with the final quantized INT8 model.
88% is much closer to the original 90% than 80% was.
Exactly. For their critical customer support application where accuracy is paramount, this 8% recovery might be well worth the increased training effort and complexity of QAT. QAT often gives them the best of both worlds, the significant size and speed benefits of INT8, but with accuracy that's very close to the original full precision model.
That's a great breakdown of the core strategies. PTQ is fast and easy, but might lose accuracy. Dynamic adapts, but has overhead. QAT gives the best accuracy, but requires retraining. It's a clear spectrum of complexity and trade-offs. But you mentioned the field is moving incredibly fast. Beyond these main strategies, PTQ, dynamic, QAT, the research community is constantly innovating, finding even more clever ways to make LLMs leaner without sacrificing too much intelligence. What are some of these more advanced, maybe more specialized techniques that are emerging, pushing the envelope even further? Give us a glimpse of the cutting edge.
You're absolutely right. The innovation pace is relentless. Beyond those three core strategies, several advanced techniques are gaining traction, offering even more nuanced control over that delicate accuracy versus efficiency trade-off. They often build upon or refine the ideas of the core methods.
Okay, like what?
One interesting technique is blockwise quantization.
Blockwise. How does that work?
Remember how we talked about per tensor, one scale ZP for the whole thing versus per channel, one scale ZP per channel row? Blockwise takes granularity even further. Instead of applying parameters to the entire tensor or just channels, blockwise quantization divides a large tensor, think of a big weight matrix, into much smaller, usually non-overlapping blocks, maybe blocks of 64 or 128 numbers. Crucially, it then calculates and applies quantization parameters, scale and 0 point, independently for each of these small blocks.
So even finer control than per channel. Different parameters for small patches within the matrix.
Exactly. This allows for a much finer granularity of control. The advantages are significant for accuracy. By quantizing at this finer granularity, blockwise quantization can often preserve the distribution of values within the tensor much better, especially if there are localized hotspots or areas with very different statistics. This often leads to improved accuracy compared to coarser methods. It also offers flexibility, as the block size itself can often be tuned as a hyperparameter to optimize that trade-off between accuracy, compression effectiveness, and the overhead of storing more parameters.
What's the downside? More complexity.
Naturally, yes. It's more complex to implement efficiently in hardware or software. And there's definitely more overhead for storing the quantization parameters. You need a scale and 0 point for every single block, rather than just one per tensor or per channel. But for pushing accuracy limits at low bit widths, that extra complexity can be well worth it.
Okay. Blockwise gives finer control. What else?
Another powerful and increasingly common approach is mixed precision quantization.
Mixed precision, does that mean using different bit widths in the same model?
Precisely. The core idea is to strategically apply different levels of precision. Maybe INT8 for some layers, FP16 for others, maybe even INT4 for specific parts to different components of the same LLM.
Why would you do that? Why not just quantize everything to the lowest possible level?
Because, as it turns out, not all layers or operations within a large neural network are equally sensitive to the effects of quantization. Some layers, if you quantize them too aggressively, say down to INT4, might cause a drastic drop in the model's overall accuracy. They're numerically sensitive. Other layers, however, might be much more robust. You could quantize them down to INT8 or even INT4 with very little impact on the final performance.
Ah, so you identify the sensitive parts and keep them more precise while being aggressive with the robust parts.
Exactly. The strategy is to keep the highly sensitive layers at a higher precision, like FP16 or maybe BF16, another 16-bit format popular in AI, while quantizing the more robust layers down to a lower precision, like INT8 or INT4. For example, in a typical transformer model, which underpins most modern LLMs, the self-attention layers are often found to be more sensitive to precision loss than the large feed-forward layers. So a common mixed precision strategy might keep the attention calculations in FP16 or BF16 while aggressively quantizing the much larger feed-forward layers down to INT8 or even INT4. This technique is all about finding an optimal balance across the entire network, balancing accuracy, speed, and memory usage by being strategic and non-uniform about where you apply your precision reductions. It's about being smart and selective, not just uniformly aggressive everywhere.
That sounds like a very intelligent way to optimize, find the bottlenecks and treat them differently.
It is, and it often yields results very close to QAT in terms of accuracy, but sometimes with less complex implementation than full QAT retraining, depending on the method used to determine the precision mix.
Any other advanced techniques worth mentioning?
One more related concept is group-wise quantization.
Group-wise, similar to block-wise.
Somewhat similar in spirit, yes. It involves dividing the weights or activations within a layer into distinct groups, and then quantizing each group independently with its own scale and zero point. The motivation is often that different parts of a large weight matrix, for instance, might learn different types of features or have different statistical properties. The numbers in one group of columns might behave very differently from the numbers in another group. By quantizing these groups separately, you can potentially achieve better accuracy because the quantization parameters, S and Z, are optimized specifically for that particular group's unique value distribution, rather than being averaged out over a larger, more diverse set of numbers. It offers a useful middle ground, finer granularity than per tensor, maybe coarser or differently structured than per channel or blockwise, giving engineers another lever to pull to fine-tune that accuracy-efficiency balance for their specific model and hardware target.
It's incredible how much research and clever engineering goes into just making these massive models efficient enough to be practical. It almost feels like a whole new subdiscipline within AI research itself. Now, all these techniques, PTQ, QATT, blockwise, mixed precision, they sound really complex to implement correctly from scratch. I imagine most developers aren't writing their own quantization code at this level.
Yeah.
Thankfully, as you hinted, there are amazing tools and libraries out there that do a lot of the heavy lifting, right? What are some of the key players in this LLM quantization tool belt that our listeners should maybe know about? The ones that make it easier for companies like InnovAI to actually put these smaller, faster models into practice.
You're absolutely right. While understanding the underlying concepts is valuable, the ecosystem of tools has matured incredibly rapidly, making it much, much easier for developers and companies to actually apply these sophisticated techniques without being PhDs in numerical analysis. There are several major players worth highlighting.
Okay, who's first?
First up, a library that has gained immense popularity, especially within the Hugging Face ecosystem, is Bit-Sambytes. This is a relatively lightweight library, but it's laser-focused on providing highly optimized, low-level routines for low-precision operations, especially 8-bit, and more recently, 4-bit matrix multiplication and storage.
So it handles the core math efficiently.
Extremely efficiently. Its key benefits are significant. It dramatically reduces the memory footprint of models. Using its 8-bit quantization offers up to a 4x reduction compared to FP32, and its 4-bit offers up to 8x. Crucially, it leverages GPU acceleration using highly optimized custom CUDA kernels, making these low-precision operations incredibly fast on compatible NVIDIA hardware. And perhaps most importantly for usability, it integrates almost seamlessly with PyTorch, which is one of the most popular deep learning frameworks.
How does it work in practice? Is it easy to use?
Often, yes, it's designed for ease of use. In simplified terms, when you load a model using Bit-Sambytes integration, it typically quantizes the model's weights down to 8-bit or 4-bit for storage and memory saving. Then, during inference, it might dequantize small chunks of weights just before they're used in a matrix multiplication, or it might use specialized kernels that can perform the multiplication directly with the low-precision weights and potentially high-precision activations. The exact mechanism can vary, but the user experience can be incredibly simple. For example, if you're using the Hugging Face Transformers library, you can often load a huge model like Bloom or Llama 2 in 4-bit precision, ready to run on a consumer GPU just by adding a single argument like load in 4-bit. True, when you load the model. Bits and Bots handles all the complex quantization and kernel management behind the scenes. It feels almost like magic.
Wow, one line of code for 8x memory reduction. That's powerful. Okay, who's next?
Next, let's talk about GPTQ, which stands for General Purpose Quantization for Generative Pre-Trained Transformers, although the technique is broader. This is a specific post-training quantization, PTQ method, that was designed explicitly for achieving high accuracy, particularly with large language models, often targeting 4-bit or even 3-bit quantization.
A PTQ method focused on accuracy. How does it achieve that?
GPTQ has several key principles. It typically performs layer-wise quantization, meaning it quantizes one layer of the network at a time, often using the output of the previous quantized layer as input, which helps minimize the accumulation of errors across the network. It's also often described as Hessian-aware, or using second-order information. This means it tries to use information about how sensitive the model's overall loss function is to changes in specific weights. It uses this sensitivity information to guide the quantization process, trying harder to preserve the weights that have the biggest impact on the model's performance. It usually involves an iterative refinement process within each layer to find the best quantized weights for that layer, given the input it receives. And it typically relies on a small calibration dataset, similar to standard PTQ, to help fine-tune these quantized weights. It's a more sophisticated PTQ approach aiming for near QAT accuracy without the retraining cost.
Okay, GPTQ is like a smarter PTQ. What else is out there?
Then we have AWQ, which stands for Activation-Aware Weight Quantization. This technique takes a slightly different philosophical approach. Instead of just looking at the weights or simulating quantization during training, AWQ focuses on the relationship between the weights and the activations they produce. It operates on the premise that not all weights are equally important. It argues that weights which significantly impact the activation values, the outputs of the layers that get passed on, are the most critical ones to preserve accurately. Why? Because those activations are what ultimately determine the model's final output. So AWQ analyzes the model to identify this small fraction of salient or important weights, often around 1%, based on observing activation statistics from calibration data. It then specifically protects these important weights from the full brunt of quantization, perhaps by scaling them differently or keeping them at slightly higher precision, while quantizing the vast majority of less critical weights more aggressively.
So it finds the VIP weights and gives them special treatment.
That's a good way to think about it. By doing this, AWQ aims for very high accuracy, particularly at low bit widths like 4-bit, by preserving the information deemed most crucial for the model's function. It's also designed with hardware efficiency in mind. Imagine InnovAI again. They need to deploy their translation LLM on a specific edge device with strict memory limits. Using AWQ might help them reduce the model size by 4x or more, down to 4-bit precision, significantly speeding up inference on that device while still maintaining acceptable translation quality because AWQ intelligently preserved the most critical parts of the model's knowledge.
Interesting. So bits and bytes, GPTQ, AWQ are specific quantization libraries or methods. What about more general tools?
Right. Moving beyond specialized libraries, we have broader inference engines and frameworks that incorporate quantization capabilities. A major one is ONNX runtime.
ONNX, I've heard of that. Open Neural Network Exchange.
That's the one. ONNX is a standard format for representing AI models, allowing them to be used across different frameworks and tools. ONNX Runtime is Microsoft's high-performance inference engine designed to run these ONNX models efficiently on various hardware platforms.
How does it relate to quantization?
ONNX Runtime plays a significant role because it has built-in support for various quantization techniques. You can take a model trained in PyTorch or TensorFlow, convert it to the ONNX format, and then use ONNX Runtime's tools to apply post-training static quantization with calibration or dynamic quantization. The big benefit here is portability and performance. ONNX Runtime is optimized for a wide range of hardware, including standard CPUs, using optimizations like Intel's 1DNN, various GPUs via integrations with TensorArt or DirectML, and even specialized accelerators. So quantizing your model within the ONNX Runtime ecosystem enables efficient deployment almost anywhere. It acts like a universal translator and optimizer for your AI model.
So ONNX Runtime helps deploy quantized models broadly. What about specifically for NVIDIA GPUs?
For maximizing performance on NVIDIA GPUs, the go-to tool is Tensor. TensorArt is NVIDIA's own software development kit, SDK, built specifically for high-performance deep learning inference. It takes models trained in frameworks like TensorFlow, PyTorch, or even ONNX models, and performs a series of aggressive optimizations tailored specifically for NVIDIA's GPU architecture.
What kind of optimizations does TensorArt do?
It does a lot. It performs aggressive graph optimizations like layer fusion, where it might combine multiple distinct layers, like a convolution, then a bias addition, then a ReLU activation, into a single highly optimized GPU operation, a kernel. This reduces the overhead of launching multiple separate operations. It performs kernel auto-tuning, selecting the most efficient specific algorithm or implementation for each operation based on the target GPU, the data types, and batch sizes. And relevant to our discussion, it has robust support for various quantization techniques, including PTQ with calibration and workflows for deploying QAT models. It can convert models to run using INT8 precision, leveraging the powerful tensor cores found in modern NVIDIA GPUs, which provide massive speedups for low-precision matrix multiplication. TensorArt's features like layer fusion, precision calibration capabilities, and support for dynamic input shapes make it incredibly powerful for squeezing every last drop of performance out of NVIDIA hardware, making your LLM inference potentially lightning fast.
Okay, Tensor for NVIDIA GPUs. It sounds like there are many specialized tools. Is there anything that ties these together, especially for LLM users?
Absolutely. And that brings us back to Hugging Face transformers.
The big library for actually using the models.
Exactly. Hugging Face Transformers is arguably the most popular library for easily downloading, loading, and working with pre-trained LLMs. While it's not a quantization engine itself, it plays a vital orchestrating role. It achieves this through deep integrations with many of the tools we just discussed. It integrates seamlessly with bit sandbytes for easy 4-bit, 8-bit loading. It works with PyTorch's native quantization features, and importantly, it integrates with Hugging Face's own Optimum library. Optimum acts as a bridge between transformers and various hardware acceleration backends, including ONNX runtime and TensorRT. This allows users to take a standard transformers model, easily optimize it, including quantization, using ONNX runtime or TensorRT via Optimum, often with simplified APIs, and then deploy it efficiently.
Right.
This whole ecosystem significantly simplifies the often complex process of applying quantization and deploying optimized LLMs, allowing developers to leverage these powerful techniques, often with just a few extra lines of code. It's the user-friendly front door that makes all this complex back-end engineering accessible to a huge community.
That's a really comprehensive tour of the tool belt. From low-level libraries like Bitsandbytes to specialized methods like GPTQ and AWQ, and overarching frameworks like ONNX runtime, TensorRT, all often accessible through Hugging Face. It makes what sounds like very complex science much more approachable for practitioners.
So let's say you've done it. You've picked a strategy, used one of these cool tools, quantized your model, and you've gotten that impressive 4x or maybe even 8x reduction in size. Your model is smaller, maybe faster. How do you actually know if you've done a good job? Beyond just the file size, what exactly do you measure to understand the trade-offs you've inevitably made? How does InnovAI confirm that their newly shrunk chatbot still delivers excellent customer service and doesn't just spout nonsense? What's the evaluation process look like?
That is the absolutely crucial next step, evaluation.
Yeah.
You have to quantify the impact across several key dimensions to truly understand if your quantization strategy was successful. Did it meet your efficiency goals? And, critically, did it maintain sufficient quality for your application? You need to know if you found that sweet spot we keep talking about. Okay, so what are the key dimensions to measure? Accuracy first, I assume.
Yes, first and foremost, you have to rigorously evaluate the accuracy metrics. But accuracy can mean different things depending on the LLM's task. For general-purpose language models, perhaps like the base model for Chatbot before task-specific fine-tuning, the most common intrinsic metric is perplexity.
Perplexity. We mentioned that before. Can you remind us what it measures?
Perplexity essentially measures how well a language model predicts a sample of text it hasn't seen before. You can think of it intuitively as how surprised or uncertain the model is by the next word in a real text sequence. A lower perplexity score is better. It indicates a model that is more confident and accurate in its predictions of likely word sequences. A low perplexity generally correlates with more coherent, natural-sounding, and grammatically correct text generation.
So, if perplexity goes up after quantization,
That's a sign that the model's predictive quality has degraded. Reduced precision might have made its internal probability calculations less accurate. If perplexity jumps significantly after quantization, it might manifest as the model starting to stumble over its words, producing text that feels slightly off, less fluent, or in worse cases, nonsensical or irrelevant. For Innov AI's chatty bot, a noticeable increase in perplexity could directly lead to more frustrating and less helpful conversations for their customers.
Okay, perplexity is a good general measure. What about for specific tasks?
Right. Beyond general perplexity, you absolutely need to evaluate using task-specific accuracy metrics that are directly relevant to the LLM's intended function. For example, if the LLM is used for question answering, you'd measure the percentage of factually correct answers it provides on a test set. If it's used for text summarization, you'd use metrics like UJG scores, which compare the generated summary against human-written reference summaries based on overlapping words or phrases. If it's for machine translation, you'd look at metrics like the BLEU score, which measures the similarity between the model's translation and one or more high-quality human translations.
So you need benchmarks tailored to the actual job.
Exactly. Quantization, by reducing precision, can sometimes impair the model's ability to capture subtle nuances, complex relationships, or specific factual details required for high performance on these tasks. A drop in these task-specific scores is a direct measure of functional degradation. If an LLM used for, say, sentiment analysis sees its F1 score drop significantly after quantization, it might misclassify customer feedback, leading to wrong business decisions. Or worse, as we mentioned, an LLM for medical diagnosis with reduced accuracy could have critical real-world consequences.
These automated metrics sound essential. Is that enough?
Often no, especially for generative tasks. Automated metrics are valuable and scalable, but they don't always capture the full picture, particularly qualitative aspects like fluency, coherence, style, tone, or creativity. That's where human evaluation becomes crucial. You need real people to read or interact with the output of the quantized model and compare it to the original or to human-generated examples.
What would human evaluators look for?
They might rate outputs based on criteria like, is this response helpful? Is it fluent and grammatically correct? Is it coherent and on topic? Does it maintain an appropriate tone? Is it factually accurate? For instance, human evaluators might rate a full precision LLM's creative story as excellent for imagination, but after quantization, they might rate it only as good, noticing a slight decrease in descriptive richness or occasional awkward phrasing that automated metrics like BLEU or Rouge might completely miss. For InnovAI's chatbot, subtle shifts in conversational flow, politeness, or the ability to handle complex user intents can make a huge difference to perceived quality, and only human evaluation can truly capture those nuances.
Accuracy is key, measured in multiple ways. What's next after accuracy? Speed.
Yes. The other major goal of quantization is usually speed improvement, so we need to measure inference speed metrics carefully. The most common metric here is latency. This is simply the time it takes for the model to generate a complete response for a single input. It's typically measured in milliseconds. Lower latency is always better, meaning a faster response. This is critical for real-time applications like chatbots or interactive assistants where users expect immediate replies.
Milliseconds matter in a conversation.
They really do. A specific component of latency that's particularly important for user perception is time to first token, TTFT. This measures how long it takes for the model to generate just the very first piece token of its output, even if the full response takes longer.
Why measure just the first token?
Because in interactive applications like chatbots or code completion, seeing the response start to appear quickly gives the user immediate feedback that the system is working. Even if the rest of the sentence takes another second, that fast TTFT makes the system feel much more responsive. Quantization can sometimes improve TTFT significantly. Then there's throughput. This measures how many requests the model can handle concurrently per unit of time. It's often measured in inferences per second, IPS, or queries per second, QPS. Throughput tells you how much load your system can handle, how many users it can serve simultaneously. Higher throughput is crucial for scaling services cost-effectively.
So latency for individual user experience, throughput for overall system capacity.
Exactly. And related to both the size and speed benefits is memory usage. This is simply the amount of memory, typically RAM on the CPU or VRAM on the GPU, required to store the model's parameters, the weights, and also its intermediate activations during inference. Quantization's primary goal, as we know, is often to drastically reduce this memory footprint. Measuring this is crucial, especially for deployment on memory-limited devices.
Like our InnovAI mobile app scenario.
Precisely. If InnovAI's original ChattyBot LLM needed 2 GB of RAM, making it unusable on many phones, but the quantized INT4 version now only needs 500 millib, that's a concrete measurable win. It directly enables the on-device AI scenario that was impossible before, without requiring constant cloud connectivity or draining the phone's battery excessively.
Okay, accuracy, speed, memory. How do we make sure we measure these reliably? Any best practices for benchmarking?
Yes, benchmarking methodology is important for getting trustworthy results. First, always use a hardware setup that's truly representative of your target deployment environment. Benchmarking on a high-end data center GPU won't tell you much if you're deploying to a low-power edge device. Second, run a few warm-up iterations before you start actually measuring. This allows the model, the system caches, and the hardware to stabilize, avoiding artificially slow results from the first cold run. Third, experiment with different batch sizes, the number of inputs you process simultaneously. Larger batch sizes often increase throughput, but can sometimes increase latency. You need to find the optimal batch size for your specific latency versus throughput requirements. And finally, always average your results over multiple runs, maybe 10 or even 100 iterations to smooth out any random fluctuations and ensure your measurements are reproducible and statistically significant. It's about getting a reliable, clear picture of your quantized model's real-world performance, not just optimistic, one-off lab numbers.
That's incredibly thorough. It's clearly not enough to just quantize and hope for the best. You really have to meticulously measure the impact across accuracy, speed, and memory using solid benchmarking practices to make sure you've actually hit your goals and haven't inadvertently degraded the user experience too much. Now, let's assume you've done all that. Your model's quantized, it's been evaluated, and you're happy with the trade-offs. It's small enough, fast enough, and accurate enough for your application. The final challenge, then, is getting it out there into the wild and keeping it running smoothly. This is where the rubber meets the road. How do we actually deploy and then maintain these optimized, quantized LLMs in the real world? How does InnoAI ensure their newly efficient chatbot continues to serve customers reliably, day after all this complex optimization work?
Indeed, deployment and ongoing maintenance are where all the theoretical benefits and careful evaluations translate into practical, real-world impact. This is about turning that optimized model from a file on a disk into a reliable, scalable, and efficient service.
Where do these quantized models typically get deployed?
Broadly speaking, you'll see LLMs deployed in one of two main environments. The first is cloud deployment. This involves utilizing the infrastructure and services offered by major cloud providers like Amazon Web Services, AWS, using SageMaker or EC2 instances, Google Cloud Platform, GCP with Vertex AI or Compute Engine, or Microsoft Azure using Azure Machine Learning or virtual machines.
What are the advantages of the cloud?
The cloud offers massive scalability. You can spin up more resources easily to handle millions of users if needed. It provides managed services that can handle much of the underlying infrastructure complexity, like load balancing, auto-scaling, and it gives you access to incredibly powerful hardware, often including the latest GPUs or even custom AI accelerators like Google's TPUs, which are perfect for running these models efficiently.
Go cloud for scale and power. What's the alternative?
The alternative is edge deployment. This means running the LLM directly on the end user's device or local hardware. Think smartphones, laptops, smart speakers, IoT gadgets, industrial robots, or even systems inside a car. These edge environments are typically characterized by severely limited computational resources, slower processors, much less available RAM, and strict power consumption limits, often running on batteries.
And this is where quantization is essential.
Absolutely crucial. For many edge deployment scenarios, running the original massive FP32 model is simply impossible due to these constraints. Quantization, by dramatically reducing the model size and often the computational cost, is the key enabling technology that allows powerful LLMs to run locally in these constrained settings, often without needing constant reliance on cloud connectivity. Think of a smart camera that can perform object recognition on board, or a voice assistant on your watch that works even when you're offline. That's enabled by optimization techniques like quantization.
Makes sense. Now, whether in the cloud or on the edge, you mentioned hardware. How does hardware acceleration play into this? Does quantization work better on certain types?
Yes, hardware acceleration is key to maximizing performance, and the type of hardware definitely influences how effective different quantization strategies might be. For standard CPUs, the general-purpose processors found in most computers and servers, optimization for quantized models often involves using special instruction sets called SING-D, single instruction, multiple data. Instructions like AVX2 or AVX512 on Intel AMD chips allow a single instruction to perform the same operation, like multiplication or addition, on multiple data points, like several 8-bit integers, simultaneously. It's like doing math in parallel on a small scale. Compilers and libraries like 1DNN leverage these instructions, along with techniques like general vectorization and multi-threading, using multiple CPU cores, to speed up quantized computations.
So CPUs can be optimized for this too. What about GPUs?
GPUs are where quantized models, especially LLMs, often really shine. GPUs are massively parallel processors with thousands of simple cores, designed for handling huge amounts of computation simultaneously. For deep learning, modern NVIDIA GPUs include specialized hardware units called tensor cores. These cores are specifically designed for performing matrix multiplications, the core operation in neural networks, at incredibly high speeds, and they are particularly efficient when working with lower precision formats like FP16, VF16, and crucially, INT8 and even INT4. Using INT8 on tensor cores can provide a massive speedup compared to FP32 on standard CUDA cores. GPU optimization also relies on maximizing memory bandwidth through techniques like coalesced memory access, reading data in large, contiguous chunks, and minimizing overhead through kernel fusion, combining multiple small operations into a single, larger GPU task, which TensorRT helps manage.
So GPUs are naturals for quantized matrix math. Any other specialized hardware?
Yes, we should mention TPUs, Google's tensor processing units. These are custom-designed chips, ASICs actually, built from the ground up specifically for accelerating deep learning workloads. They are known for being highly efficient, particularly with quantized models, often using BF16 or INT8 internally, and are primarily available through Google Cloud. And for the absolute highest performance or energy efficiency in very specific high-volume applications, companies might design their own custom hardware using FPGAs, field-programmable gate arrays, which are reconfigurable, or ASICs, application-specific integrated circuits, which are fixed. These can be tailored precisely for running a specific quantized model architecture with maximum efficiency, but involve much higher development costs.
Wow, a whole spectrum of hardware. What's the key takeaway here?
The key idea across all these hardware types is that the optimal quantization strategy, the bit width you choose, the specific technique, PTQ versus QAT,
Hmm?
the granularity per tensor versus per channel versus blockwise, often depends heavily on the target hardware and its specific capabilities and limitations. A strategy optimized for a high-end NVIDIA GPU with tensor cores might be very different from one optimized for a low-power ARM CPU on an edge device. You need to quantize for your target.
Got it. Target the hardware. Now, once the model is deployed, whether on cloud or edge, optimized for the hardware, you can't just forget about it, right?
Yeah.
How do you monitor these things in production?
Absolutely not. Deployment is just the beginning. Monitoring quantized LLMs in production is vital for ensuring continued performance, reliability, cost-effectiveness, and crucially, that the accuracy hasn't degraded unexpectedly over time.
What key things do you need to monitor?
You need to keep a close eye on several categories of metrics. First, accuracy. You need ways to continuously or periodically assess if the model is still performing as expected. This could involve monitoring intrinsic metrics like perplexity on live or sampled data. More importantly, it involves tracking those task-specific accuracy metrics, e.g. F1 score for classification, ODG for summarization, maybe user feedback scores. You're looking for drift, a gradual degradation in performance, perhaps because the real-world data the model is seeing is slowly changing from what it was trained or calibrated on. You also might want to monitor model calibration, how well the model's predicted confidence scores align with its actual accuracy. Second, performance. You need to track operational metrics like average and percentile latency, your GP95, P99 latency, to ensure responsiveness. Monitor throughput, QPS, to understand load and capacity. Keep an eye on memory usage and CPU utilization to spot inefficiencies or resource exhaustion. Third, basic system health. Monitor things like server error rates, are requests failing, resource availability, is the disk full, is CPU pegged at 100%, and maybe even hardware health indicators like temperature or power draw, especially on edge devices.
How do you make sense of all that data?
The best practice is to establish baselines for all these key metrics right after deployment, representing the expected performance. Then, define clear thresholds or acceptable ranges for each metric. If a metric crosses its threshold, GP99 latency exceeds 500 meters, or task accuracy drops below 85%, it should trigger an alert, signaling to the operations team that something needs investigation. For example, InnovAI, after deploying their quantized chatty bot using maybe a mixed precision QAT strategy, would continuously monitor its latency, throughput, error rates, and perhaps periodically evaluate its sentiment analysis accuracy on recent conversation logs, using tools like Prometheus for metrics collection and Grafana for visualization and alerting. This allows them to catch problems before they significantly impact customers.
Okay, monitoring is crucial for catching issues. What about proactively maintaining these models?
Yes, maintenance is the ongoing effort to keep the model performing well because the world, the users, and the data are constantly changing. This often involves regular model updates. As new data becomes available, or as model performance starts to drift, you'll likely need to retrain or fine-tune the model, potentially including rerunning QAT if you use that, with this fresh data to keep it relevant and accurate. Debugging is also an ongoing reality. Common issues with quantized models in production include unexpected accuracy degradation, which might point to a calibration mismatch with the live data, or the model encountering out-of-distribution inputs it wasn't prepared for. Numerical instability, seeing weird nan, not a number, or infinity values, sometimes due to aggressive quantization hitting edge cases.
Hmm.
Performance degradation may be due to changes in input data patterns or system load, or just generally unexpected or biased behavior. Debugging these often involves careful layer-wise analysis, examining activation distributions, histograms, detailed error analysis on problematic inputs, and potentially adjusting the quantization strategy itself. And finally, when deploying these updates or new versions, having robust deployment strategies is essential. Techniques like canary deployments, gradually rolling out the new quantized model version to a small percentage of users first, monitoring it closely before wider release, and having solid rollback mechanisms, the ability to quickly revert to the previous stable version if the new one causes problems, are critical for minimizing risks and ensuring a smooth, uninterrupted user experience. So, to wrap up our deep dive today, what's truly fascinating, I think, is how quantization has really evolved. It's transformed from being this somewhat niche optimization technique, maybe used in embedded systems, into an absolutely indispensable tool for making these powerful large language models practical, affordable, and accessible everywhere. It's this careful, often intricate balance between shrinking these colossal digital brains, making them faster and cheaper to run, while fighting hard to preserve their incredible intelligence and capabilities. And thinking about that balance, this raises an important question.
That's a powerful summary, and yeah, something I've definitely been thinking about throughout this whole deep dive. It really hammers home that trade-off. As these LLMs continue to grow exponentially in size and capability, we hear about models with trillions of parameters now, and as we relentlessly push them onto every device imaginable, from our powerful cloud servers down to our phones, our watches, maybe even tiny IoT sensors, how much precision do we really need in the end? Is FP32 always the gold standard we should strive for, or is good enough precision achieved through clever quantization actually the key to unlocking the next wave of AI? And perhaps even more intriguingly, what new forms of intelligence, what completely revolutionary applications might emerge when these incredibly powerful models become truly ubiquitous, running efficiently everywhere, precisely because of these clever optimizations like quantization? Will we see a new era of ambient, seamlessly integrated AI that's just always there, even on devices we can't really imagine today? It's definitely something to think about. We encourage you, our listener, to mull that over.
What stands out to you the most from this deep dive into quantization? What further questions does this spark for you as you consider the future of AI and how it might impact your own devices, your work, and your everyday experiences? Thank you for joining us on this deep dive into the world of LLM quantization. We hope you feel a little bit more well-informed, maybe a little less intimidated by the jargon, and perhaps even more curious about the incredible engineering happening behind the scenes of the AI revolution. We'll see you on the next deep dive.